This is Team 4's interim presentation by Brendan, Eddie, Rebecca, Drew, Sam, and Josiah, where we analyze a drill press for DFA and DfM. Background on a tabletop drill press, which are commonly used to drill holes into materials such as metal, wood, and plastic. A motor drives the spindle to rotate an end mill or drill bit to create precise holes within the working material. A drill press provides control and precision to the user with low cost and minimal training when compared to a mill. The primary consumer of the drill press are those who own small workshops for metalworking, woodworking, garages for cars, and general engineering needs. These are also purchased by secondary consumers such as hobbyists and DIYers who work on at-home projects outside of the professional setting. The global market was 889.4 million US dollars with a compound annual growth rate of 4.15% in 2022. There are an estimated 254,000 drill presses sold globally per year based on an average price of $3,500. Pictured here is an exploded view of the drill press with its various components. Note the screws and nuts are not shown within this image.
Within the Function Analysis System Technique, or FAST diagram, we describe the one main task function for our tabletop-sized drill, as well as the basic and supporting functions to answer the question, how does the product or the drill press perform the task function of creating holes?
We prepared two assembly sequences for our drill press. In our fishbone diagram, we will be moving the assembly process from left to right, with the image on the top right-hand corner showing our assembly process. In assembly sequence 1, we start with the base plate, add a column, attach a table lock, add a sub-assembly of the table lock lever and lever handle ball, attach a table, add the neck, add a driving cone, add a pulley frame, and insert a large sub-assembly of the spindle, stop collar, flange, spindle cone, and sleeve. And finally, we attach a hand lever bracket. In assembly sequence 2, we start with the neck, add a column, attach a sub-assembly of the table lock, table lever handle ball, and table lock lever, mount the assembly onto a base plate, add a sub-assembly of the spindle and sleeve, and add another sub-assembly of the spindle cone sleeve, flange, and stop collar, add a hand lever bracket, attach a driving cone, and finally attach a pulley frame. Compared to two sequences, we found that Sequence 1 was a better assembly process due to the ease of transferring, handling, and locating parts, along with the ease of testing assemblies.
Using both the fishbone assembly diagram from the assembly sequence and the FAST diagram, we created a function component mapping matrix to determine the functional purpose of each component of a drill press. The names of each component, excluding the fasteners, can be found in the leftmost column. Each terminal function from the FAST diagram can be found along the top row. If there is an X in a cell, it means that the function is realized by the component in the corresponding row. Using this matrix, we are able to determine the functional importance of each component of the drill press.
This is our bill of materials. We assumed an annual production rate of 50,000 units, and the costs of the components were calculated using hubs.com when applicable, as well as manual calculations based on current material unit prices. We assumed manual assembly, as well as a labor cost of $19 an hour, the median U.S. assembly line worker wage. Our parts were manufactured using a variety of methods, including CNC machining, die casting, injection molding, and more. Our total cost reached $81.98.
Using the function component mapping matrix in the bill of materials, we organized each of the components of the drill press into the quad chart. The chart organizes the components into 4 categories based on cost and functional importance. We determine the cost of each component using the bill of materials, and the functional importance of each component using the function component mapping matrix. The components that are of high cost and high functional importance are the ones in which DFMA should be applied.
For the product family design, we'll cover a few slides relating to the functional differentiation table, component commonality table, CAD for modules for primary and secondary customers, common interface, and product family assembly diagram. The functional differentiation table is based on the FAST diagram branches shown in the slides before. The functions that differ between the customer groups are just size and hold product. The components commonality table references the function component mapping matrix shown before, and the modules that change are the table, neck, and table lock.
As we can see in these two figures of the CAD for the primary and secondary customers, the primary customers has a drill press with an enlarged size in the neck, table, and table lock, and additional holes in the table for mounting and holding product. In the secondary CAD file, you can see a reduced size in the neck, table, and table lock, and only one hole in the table for mounting and holding the product. For these two family assembly diagrams, the first one shows the original assembly sequence. This product is built on a ground-up type of assembly, so we see that the base and column all the way down to the hand lever bracket is the order in which it is assembled. Shown in red are the parts that are changing, and that is why they have two different variations. In a modified assembly sequence, only the table has moved to the very end. Since this is a ground-up assembly, as previously stated, it is difficult to modify the table lock and neck to delayed differentiation because other parts are built based on those two.
That is the end of our interim presentation. Thank you for watching.